IIW India is a leading welding institute in India, and it's headquartered at Kolkata, but having a lot of branches like Mumbai, Bangalore, Chennai, Pune, etc. So yeah, this webinar is being organized today by the Mumbai branch. Move to the next slide. Next slide, please. What are the major objectives of? We are now talking of the major objectives of the Indian Institute of Welding. So I'm just talking about that. It assists human resource development in welding in India. It works for the
Headquartered
technology
at Kolkata,
diffusion
but
in the
having a lot of
industry.
branches like Mumbai, Bangalore, Chennai, Pune.
There is some technical glitch. Yeah, now it is okay. So IIW India also fosters R&D in welding in India. It also promotes health and safety related aspects in welding. It also has having major objective to establish international standards of quality for the Indian fabrication industry. Next, which what are the different activities that adds value to welding professionals? IIW India conduct technical meetings, workshops, and industry-oriented training programs at the national as well as at the branch level. We also organize seminars, conferences, and exhibitions on welding and allied technologies. We have a Indian Welding Journal wherein a lot of technical articles get published quarterly in collaboration with AWS, that is American Welding Society, and a monthly newsletter is also being run, which can also you can see a lot of details on the website www.iiwindia.com. Further activities, we also run welding training and certification like international welding engineer, international welding technologist, international welding specialist, and many more. How we are catering to the career opportunities by means of skill councils, that is by means of skill development programs like automotive sector skill council, capital goods sector skill council, Indian iron and steel sector skill council, different skill councils that we are working hand in hand for the skill development, particularly welders. So these are one of few more major activities. When it comes to technology diffusion, as I've already mentioned, Indian welding journals, branch and national level technical programs, skill development programs, conducting AIW examinations, also conducting national level welder training and certification programs. We also help manufacturers with the ISO 3834 audit requirements and conducting it. We also help train the trainers kind of program we run. Welder competition, both male and female, we run, and many more other activities are being run by IIW India. These are the few benefits of being a member of IIW India. You can take advantage of several courses and examinations, and that will help you develop your personal career in welding, acquire and disseminate knowledge in welding, useful networking with fellow national and international experts like what we are having today is an international expert speaker. So you are able to learn from them today by means of a webinar. Free access to quarterly published Indian Welding Journal, concessional charges to the members and for the workshops or the seminars, and many more benefits. These are in the next slide, you will see types of membership details, what are the different categories of you becoming a member. So whosoever is not a member and is willing to be a part of IIW, we are there to help you out. So this is just for your information for becoming a member. These are the membership fee structure, how it is like that. So you can take it as a reference, or you can reach out to Mumbai branch or relevant branches across the nation to become a part of IIW India. Next. This is the, if you as an organization would like to become a part of IIW, you can take it as an option of ICM, that is Industrial Corporate Member. So these are the details of that on the slide you can see. And yeah, with that, I come to the end of this brief of IIW India, its activities. And these are the contact details of IIW Mumbai branch. You can contact Mr. Sachin Surve, our office bearer. And this is the mail ID. For any of your queries, feel happy to reach out to us. Thank you. With this, I hand over to Mr. Krishnan for the introduction of the speakers. Thank you.
Yeah, good morning, Chris Weissman and Mr. James Redman.
Good morning.
Yeah, good morning.
Morning.
Yeah, the warm welcome from our side, from Indian Institute of Building Mumbai branch for this tech talk. Let me start a brief introduction regarding Chris Weissman. Uh, Mr. Chris is a material scientist and has spent almost 30 years in R&D career with a global aluminum producer. The technology areas to which he has contributed include corrosion, thermomechanical forming, novel test methods, plant process optimization, and joining and surface treatment, etc. And Chris joined TWI in 2007 and is the corporate membership manager for both the aerospace and equipment, consumable and material sectors. He has an additional geographic responsibility for TWI industrial members in India and in supporting TWI's ambitions right down here. So most of you might have seen him at various conferences and seminars and exhibitions in India. He is a very frequent visitor. Today, his role is focused on developing technical and commercial opportunities for TWI and its customers all around the globe. Thanks, Chris, for accepting our request for the seminar and also helping me to arrange this in a very proficient way. Now, let me introduce Mr. James. Yeah, Mr. James Redman joined TWI in September 2012 and is a principal project leader in the thermal processing technology section, and he has almost 9 years of working experience as a material engineer, as well as he has honors in engineering from the University of Sheffield in this particular field. James has been carrying out diffusion bonding projects and research for almost 3.5 years and has led the research program for the development and patenting of this surface preparation technology that enables aluminum diffusion bonding. James leads TWI's diffusion bonding technology offering, of which, in fact, TWI has more than 6 decades of experience and has investigated a multitude of different alloys and joining techniques. So it is a real pleasure to hear more from Mr. James. And over to you, Mr. James, for a wonderful session on diffusion bonding.
Thank you for the introduction.
So will James present our slides?
Yeah, James, I have made you the host for the session now, so you have the access to share your screen.
Excellent. Right, just loading up now. Okay.
We are live on YouTube as well at the moment, so that those members who cannot reach us or connect us through Zoom, they would be viewing it there. And once it's completed, I'll share the link with the rest of the people who have registered but not been able to join. Thanks, James. Over to you.
Okay, so before we have James, it's my job to, because I made James work on a Saturday, I have to do a little bit first. So thank you very much, everybody, for inviting TWI to this event. And I'm very glad that I just had the pleasure to beat the COVID virus in February. I just about managed to get into India. And normally I would come back to India about this time of year to warm my bones. So we're missing you already. So it's great to reconnect. With the Indian Institute of Welding, as many of you know, I believe there is much more we could do together. And I know some of you think the same. And maybe events like this are a great way for us to maybe reassess how we maybe collaborate together in India. And in particular, as the UK changes its stance vis-a-vis things like Europe. So next year, I think the openings for India and the UK are really going to start emerging. So very quickly, because many of you do know us, I will just give you a brief introduction to TWI. Next slide. Thanks, James. So just like yourselves, we're membership-based. I don't believe we have nearly as many individual members, but we have many commercial and industrial members. And we have about 700 to 750 companies around the world. We're very international. Most of our members, industrial members, are outside the UK, about 66%. We have a lot of manufacturing space, so we're very often used in things like prototyping, and we do a lot of training, just like IIW. So I think going forward, there's going to be scope for, maybe exploring avenues like training together, and particularly with trying to maybe encourage TWI in particular to Indianize some of its products for the Indian market. And I think IIW could guide us very much in that way. We're quite large. We have 850 staff and we have 18 facilities around the world. These are our UK research centres. James and I are based in Cambridge. We haven't seen that place for a long time now, but it's still operating very much on the technical side, but many of us are working from home as well. We have specialisms around the country, one up here in Rotherham in the northwest of England, for example. We do a lot of additive manufacture there, and we also have the world's most powerful friction stir welding machine. I think this area down in Port Talbot in Wales, it's very specialized in NDT and in things like how do we apply NDT to Industry 4.0. So a lot of work going on there in, for example, continuous NDT. Next slide, please, James. And because most of our members are outside the UK, we have facilities, offices, and particularly training schools around the world. And in India, our main office and training school, as many of you may know, is in Chennai. Next slide, James. Just very briefly, what does TWI do? We're known as the Welding Institute, and all forms of joining you can find at TWI. But interestingly, we are not just about joining these days. So we do a lot of work in surface engineering. We do a lot of work in coatings, getting functionality on the surface. And we do a lot of work in failure analysis and metallurgy, and these days a lot more in polymers. But it's a very broad animal. However, joining is very much our core business still. Just a quick mention of TWI in India. We've been delivering skills there for many, many years. But in 2012, we actually opened our own business down in Chennai. And we're training currently around about 1,500 engineers a year. We have an international accredited suite of training, which is quite popular in India, known as CSWIP. However, I think the scope for India, for TWI in India, is to do things outside of CSWIP, and particularly towards the Make in India campaign. So hands-on kind of skills. And an interesting thing is most of our international members, of course, are either in India or investing to go into India. This is our facility in Chennai. I don't know if any of you have been there, but it goes back quite a way. So it's actually bigger than it looks on the outside. And we have about 30 local Indian staff trained up by TWI in delivering courses in Chennai. But they also deliver around the country. And I think that national thing is something IIW and TWI could do more of. Let's talk about that another day. Next slide. Just a quick mention, these are some of our industrial members. Krishnan has kindly invited us to this event. And in fact, Larsen and Toubro were our first ever industrial member in India, quickly followed by Godrej and Boyce. And they are key drivers historically of anything that TWI does in India. Next slide. But for me, one of the most important, interesting aspects of our delivery of services in India is some of these international companies, nearly all of them are partnering in one way or another with Indian companies. So a classic one is Mahindra and BAE, for example. And I think this is offering TWI a lot more scope to do something useful in India, in particular to help possibly with some of the supply chains. So the kind of technology that James is talking to you about today is basically coming to India if it's not already there. So people like Bharat Forge will already be interested in it, but some of these international companies will be trying to technology transfer this kind of technology one day into India. Next slide. And very quickly, these are the kind of partnerships we already have in India. So we do work with CII. We're very lucky to get invited to IIW events, but I still believe we could do more. We've done some interaction with MSME, and more recently, particularly on automotive, we've been doing collaborative type activities with ARAI. And there is a UK driven program in the UK driven by the Indian Commission, High Commission in London, and it's called the Access India program. And this is actually encouraging SMEs in both countries to work together, and TWI gets involved in that too. Next slide, please. So you've already been advised. Thank you for listening to me. Just a few tips there on the webinar. I'd like to introduce you now to James and wish you have a very interesting webinar from James on diffusion bonding. Thank you, James.
Thanks, Chris. Thanks for the introduction there. So yeah, good morning, good afternoon, or good evening to everybody who's taking the time to dial in today. Chris will probably be a bit unpleased to hear it's actually sunny here now. I might have to close the curtains a little bit, but there are some ominous grey clouds in the distance I'm keeping an eye on. So I'm supposed to be going to a football match this afternoon, so we'll see how that pans out. But anyway, today I'm going to be talking to you guys about diffusion bonding and its opportunities and challenges. So the agenda today is I'm going to firstly give a brief introduction to my background, go through what diffusion bonding actually is, what we do at TWI on diffusion bonding, and I'm going to give a relatively detailed example of diffusion bonding of aluminium alloys, because it's an interesting new field that we've recently developed. I will then go through some more generic applications, a couple of case studies, then open up the floor to any questions. So my background, I was an undergraduate at the University of Sheffield studying materials science and engineering. And in the third year, I had an industrial placement at Tata Steel based in Scunthorpe. While I was there, I worked in the rail technologies team, so mainly focused on qualification testing for high performance rail. But I also got involved in a lot of inspection of worlds and categorization of failure modes. So it's a really good placement. And I also done a lot of site work where I walked up and down the rails of the East Midlands, measuring wear on track, and particularly high wear locations such as sharp curves or track which has lots of high tonnage freight. So I graduated from the University of Sheffield in 2012, and I went straight to TWI, working in the materials, performance and ferrous alloys team. I was in this team for 5 years, and to really sort of distill down what I'd done in those 5 years, I'd done a lot of work on failure investigations, where I must have looked at probably 30 or 40 different failure investigations and looked at all sorts of different components. And there was a lot of research I carried out on more sort of basic ferrous metallurgy type studies. And I was also involved in corrosion testing and sour testing, so things like hydrogen-induced cracking and sulfide stress cracking testing. And towards the end of my time, I actually got involved with our hydrogen testing. I actually managed the hydrogen lab for about 6 months. And we've got quite a unique facility at TWI where we can test parts in high pressure hydrogen, so 1000 bar at about 150 degrees Celsius. So lots of interesting work categorizing different grades of materials and investigating how materials behave if they got welds in them or slightly different microstructures. So that was really interesting. But in 2017, a really good opportunity came up in the specialist materials joining team, which I couldn't really turn down. It's now called the thermal processing technologies team. So, and what really drew me was diffusion bonding and vacuum brazing. They're two technologies I've always been aware of and really interested in. And having the chance to work in a team which operates this equipment was too good to pass down. I also do some other sort of more unusual things in the background. I do a lot of work with micro joining, so sort of electronics type joining projects, looking at soldering, discharge welding, wire bonding, and ultrasonic. And we also do a lot of work developing dissimilar materials joining, quite often with a heavy bent towards ceramic materials, trying to join ceramics to metals, for example. This is a brief overview of the thermal processing technologies team and the equipment and processes we cover. So what's fusion bonding, which I'll talk about more today. We do a lot of work with brazing, and probably 90% of our brazing work is vacuum brazing. And you can see on the top right hand side, I'll probably get the laser pointer, I can get that to work. There we go. So this is our large industrial scale vacuum brazing furnace, which is roughly about 1 meter cubed working zone. And we also have two smaller scale vacuum brazing furnaces, sort of laboratory scale. We do infrequent work with flame brazing. We do have a brazing hearth and gas sources to do that. And we often get involved with induction brazing as well. Micro join I've kind of already covered. The bottom right image over here is wire bonding machine we have. But we also do work with powders and coatings. We have a subsection of the team. There are 3 people working on powder categorization. And by that, I mean looking at the shape distribution and size distribution of particles before they are 3D printed. And we also have a lot of, we set up a nickel plating facility recently. We're doing lots of research into alternative and more novel type nickel plating processes. And finally, I've already covered ceramics. We cover our ceramic technologies at TWI. So joining questions, any sort of consultancy, be it failure investigations or processing questions. So that's a brief introduction there, but now I'm going to go into what we actually all came here today for, which is talk about diffusion bonding. So diffusion bonding is a joining process, and traditionally it's been used for more sort of niche applications. And by that, I mean components which either have a complex geometry or where you're trying to join two materials which are difficult to join using more traditional methods. For example, when you weld certain materials together which are not compatible, you can form intermetallic particles which make the joint very brittle. So when you've got these issues, diffusion bonding could become a joining technology which is applicable. But to put into sort of basic layman's terms what diffusion bonding actually is, you take 2 pieces of material, typically with a machined face, you squash them together under load and under heat, and they become a solid block of material. Because we're heating these parts up, we typically do this in a protective atmosphere. So that could be a lack of atmosphere or a vacuum, or we could use an inert gas such as nitrogen or argon. And there also is some research being carried out looking at active gases. So a partial pressure of hydrogen could also yield some advantages. But on the right-hand side, you can see a sort of pictorial representation of what happens during diffusion bonding. So when you've got a surface, even if it looks sort of really polished and flat, when you look at it closer up, it will have a rough surface. And these look a little bit like a mountain range, and these are called asperities. So the first thing that happens when you're applying the load and the heat is these asperities or micro asperities begin to deform. Then you sort of start to get plastic deformation processes take over, sort of creep type processes. Most materials will have an oxide layer on the outside, and that at the temperature of diffusion bonding, these will then begin to diffuse into the parent material. Finally, at the end, you have the surface oxides, the vacancy diffusion mechanisms begin to take over, and the small pores we've got get smaller and smaller until if you've got the parameters correct, the diffusion bonded joint is almost impossible to resolve. So I'll give an example on the next slide. So these were two different plates of material, and this is where the bond is. And as you can see in this micrograph, the bond is very difficult to resolve. You can just about make out a few tiny micro voids just here. So what I would also add, this property of diffusion bonding is what gives it such a wide range of potential applications, which I will discuss in later slides. So this picture on the right hand side, this is our diffusion bonding facility at TWI. And what it essentially is a vacuum furnace with a ram through the center. And because it has a ram, a hydraulic ram, this is called uniaxial diffusion bonding. So just looking at the question there. Yeah, so this is a unique facility in the UK. I call this a medium scale diffusion bonding furnace. And by that, I mean, it's not an industrial sized piece of kit, but it's not laboratory sized either, which means we can get some pretty large parts into the furnace. The working zone is 300 millimeters by 360 by 400. We can go up to 1,600 degrees Celsius, and the hydraulic ram going through the center can apply up to 35 kilonewtons of load. This furnace 99% of the time is operated in a vacuum, but it can be, we can put a backfill of an inert gas in there if we need to. There are certain situations, which I will discuss, where a partial pressure is beneficial. It's to do with something called vapor pressure of certain alloys. Certain materials will vaporize at high vacuum. So the hot zone is graphite lined, and we can actually modify the chamber for larger parts if we need to. I see there's a few questions. Let's quickly have a look at those. So yeah, the advantages over conventional welding processes, I will sort of go into that a bit later. How do the surface oxides dissolve? Basically, yeah, so I'll go into this slightly in another slide, but the temperature at which we carry out diffusion bonding is such that it's a high enough temperature, high enough energy to dissolve the oxide into the parent material. For certain grades of material, as I will discuss, aluminium being one of those, the temperature of diffusion bonding is not high enough to dissolve the oxides, and oxides is a really big challenge, so I will go into that. And what's the maximum thickness we can weld? Obviously, I'll cover that in another slide later, so I'll come back to that question eventually. Right. There you go, right. So I think at this stage, I've given a bit of background on diffusion bonding, but I think it's a good idea to give a application at this point so you can visualize what you can actually do with this process. And one of the things we mostly work on is the manufacture of heat exchangers, or I should say compact heat exchangers. So what we do is on the top left here, we have what are called shims, and these have a pattern etched into the surface, often with a photochemical process. Excuse me. So it's called photochemically etched. We stack these together, and when you diffusion bond it, you get a complex 3D structure, as you can see in the bottom left. These compact heat exchangers have advantages over traditional sort of tube-to-tube sheet heat exchangers because the channels are closer. If you look on the bottom right here, this is a micrograph of this heat exchanger, and you can see how close the channels are. So this layer here will be the hot fluid, the layer below will be cold fluid, and vice versa. So you can see the small distance the thermal heat has to transfer before it goes into the cold fluid. So because the channels are closer, they're more efficient, but because of the diffusion bonded joints, which I previously showed, which are almost invisible, the strength you can get from them can approach parent material. So you can actually run these at higher pressure as well to increase your efficiency. Because of the way we can use diffusion bonding and these sort of shims, I like to think this is an additive process because you're adding several building blocks together to create a final part. And there's sort of a lot of design, you can express yourself quite a lot of your design of these shims. So I think of it as an additive process. Not traditionally speaking a traditional additive process, but it's a quasi additive process. So this sort of pie chart represents the three main areas that we work on at TWI with diffusion bonding. First one is research. We do a lot of work on basic research and diffusion bonding, some of which is funded by our internal core research program, and some of which is funded by clients. But this can range from desk-based studies, so that's looking at literature reviews, all the way through to in-depth metallurgical studies and joining trials. We also do a lot of work on surface preparation. As one of the questions already alluded to, oxide is an issue, so how you prepare your surface is an important consideration. So we also do a lot of work with process development trials, and we have a standard approach where we'll start to investigate. What's this? Sorry, I've got some more. Yeah. So with the process development trials, we start off with simple geometries, and we develop our parameters. Then we go to sort of larger heat exchangers. So we go from smaller to larger, because with the smaller samples, you're trying to develop your parameters and work out the strength of your bonds. And we typically investigate our bonds by mechanical testing, metallography and microscopy, and even corrosion testing. So we can sort of, and then we finally scale this up to prototype full-size units. Right, and the final thing we sort of work on is consultancy. So we do general sort of help with our clients designing assemblies. We look at different ways of heating the parts. That's quite important. And we do also carry out failure analysis and testing and qualification programs for our customers. So what materials can be diffusion bonded? Well, luckily for us, most common engineering materials can be diffusion bonded. And at TWI, we have looked at most materials. We've actually been diffusion bonding since 1966. And we've looked at all different types of ferrous alloys, so carbon steels, stainless steels, ODS, nickel alloys, such as Inconels, the more exotic nickel-based and cobalt-based alloys, such as Haynes alloys, titanium alloys, copper alloys, aluminium, and also looked at zircaloy and zirconium. And we've also investigated ceramic materials and metal matrix composites. And what we generally do, we develop the furnace parameters and the surface preparation requirements, which I'll go into more in the next slide. So when we're diffusion bonding, there are two sets of parameters, really. There's the furnace parameters, which are the time at which you hold, the temperature you go to, and the amount of pressure you apply. So I've put loads there. It's actually incorrect. It's pressure, but load is a function of pressure. And also the other two parameters are the surface finish of the components and the atmosphere at which you diffusion bonding. So at TWI, we have a general approach where we use a lower load or lower pressure and a longer hold time. And the reason for that is the limitation of our furnace. As I've already explained, we have a 35 kilonewton maximum load, so that often limits the pressure we can apply, especially if we have a large surface area component. But if you work in a laboratory, quite often you'll be working on smaller coupons, which allows you to apply a much higher load and increase the heating rates and the cooling times. But we tend to go for the lower load, longer hold time approach. And to give you just a bit of a feel for some of the parameters, the temperature at which we bond is typically 60 to 80% of the melting point of the material. And by melting point, I mean the solidus. So some materials have a range of melting points. We'd go for the lowest one, so the solidus. The applied load is typically 1 to 10 megapascals. And in certain applications where you have intricate internal features, you want to limit plastic deformation of those. So you're trying to balance pressure versus functionality. The time where you can go to infinity, but typically diffusion bonds are 1 to 4 hours in our furnace. And like I said before, we often do this in a vacuum or a partial pressure of inert gas. The surface roughness parameters which are important are the surface roughness, or RA. The smoother the surface, the better the diffusion bonded joint afterwards. But flatness and parallelism are also very important. You can have a very smooth surface, but if it's not parallel with the face you're trying to join, you're going to get a huge void present. So surface finish is very important. So yeah, the other important consideration is which interlayers you use. What I will say at this point, most materials you can diffusion bond with no interlayers. You don't need any, but there are certain combinations, particularly dissimilar materials, where an interlayer is required. That's typically to disrupt or react with the oxide layers which are present in the parent material. So talking of oxide layers and interlayers, I'm going to spend one slide talking about a process called transient liquid phase diffusion bonding, or TLPDB. So this is slightly different to solid state diffusion bonding because we put in a thin interlayer of material between the two parts we're trying to join, and this will form a molten phase at a lower temperature than the parent materials. So essentially we're trying to melt the interlayer but not the parent material. So it's kind of like brazing in a way, but you're applying a pressure and a load to the part, and you can get away with much thinner interlayers. What you can also do with certain material groups which are compatible, you can form a eutectic phase between the parent materials, and you can try to utilize this to get a small molten zone between the two materials. Off the top of my head, something like gold and tin forms eutectic, or copper and aluminium. But anyway, TLPDB can be used as a strategy to join dissimilar materials or materials which are difficult to join using solid state processes. So the liquid phase that we try to create spreads along the interface, and it completely diffuses into the bulk material, and the actual resultant joint is invisible. Here is an example at the bottom. That's where the joint was. And you can see when we did the tensile testing, the joints around here actually failed in the parent material. So we got higher strength in the joint compared to the parent material. Just quickly check the questions again that are coming in. So someone's asked, is friction stir welding a type of diffusion bonding process? I'd say no, it's not, because friction relies on high yield, high strain approach, where diffusion bonding is no sort of it's no mechanical load, it's just a uniaxial load. And the reason for the load, it doesn't necessarily do anything, it's just to get the two interfaces into intimate contact. That's the whole reason for the load. The closer the materials are and the more you have in contact, the better the bond. So that's what the load does essentially. So they are different processes. So yeah, because diffusion bonding is carried out at high temperatures, it can have an impact on the base material you're trying to join, and it also can have an impact on the design of your components. So we do a lot of work with our diffusion bonding development programs on verification and categorization, and these often feed back into the design process of the parts, and also provide us with confidence in the process, and allow us to determine if any post-processing is required. For example, certain materials, once you heat them, become very soft, they become annealed. So you might want to do a post-diffusion bonding heat treatment. So some sort of heat followed by a quench, followed by an aging perhaps, for example. So yeah, some of the verification techniques we use, the most basic yet the most powerful is sectioning and microscopy. From this, we can see the actual joints themselves. We can assess the level of porosity if there is any. We can see if there are any phases which are formed and analyze them using scanning electron microscopy, or the EDX function more specifically. But yeah, from metallography and microscopy, we can get an awful lot of information about our joints. But the problem with that is it's not a mechanical test. So we do a load of different mechanical testing, ranging from tensile through to fatigue. If you look at Sharpie impact, what I would say with Sharpie is we don't often do that on the bond itself, because trying to target the bond is almost impossible. But I'm talking more about Sharpie testing of the parent material. We also can do leak testing if the component geometry allows it. We can do a helium leak test to see if it's leak tight, and also pressure testing to see if it can withstand the service conditions. Finally, NDT is also an option, so ultrasonic inspection. But if you have a complex internal 3D structure, NDT can be very challenging. So just looking at some more questions. Will diffusion bonding be useful to join single crystal alloys to polycrystal alloys without affecting single crystal properties? Yeah, it's something I'm wanting to look into. I'm not looking at single crystals as such. I'm looking at columnar crystals. But yeah, it's one of those things where it depends on the material grade, and you'd have to sort of try to work out a set of parameters where you're not affecting the microstructure. I think it's going to be quite challenging. I think when you apply the heat and light, the material will probably recrystallize. But yeah, it depends on what particular alloy you're looking at. So here are a few example activities of what we do at TBI. So I've spoken about compact heat exchangers. There's also we've done quite a bit of work on transient liquid phase diffusion bonding. We're often looking at joining refractory metals and ceramics as well. We've also been carrying out diffusion bonding studies on additively manufactured parts recently to some quite good success. I'm also trying to get our inert gas set up in place. We can do it at the moment manually, but we're trying to get a more automated process in place. Right, so that's sort of a brief introduction of diffusion bonding. I'm going to now go into more details of a particular type of diffusion bonding. This is for the diffusion bonding of aluminium alloys. So firstly, diffusion bonding of aluminium is challenging, but diffusion bonding for other materials is well established. The reason it's difficult for aluminium is because of the oxide layer, but you're probably asking yourself, don't other materials also have oxide layers? And that is correct, but there's a difference here. Because aluminium alloys have a low melting point, you cannot heat the material to a high enough temperature to dissolve the oxide. In doing so, you would melt the aluminium, which is useless. So that's the problem we're trying to overcome. But there are more issues with that. So because the actual temperatures for diffusion bonding aluminium, say, versus titanium, they're lower. So titanium diffusion bonds somewhere between 800 to 1,000 degrees Celsius, depends on the grade. Aluminium, you're about half that, well, sort of between 500 to 600, depending on your grade. So diffusion bonding is a diffusional process, and the biggest driver for diffusion is temperature. So if you're bonding at a lower temperature, you're getting less diffusion. So that's an issue. So then to promote diffusion between the parts, we actually increase the temperature to much closer to the melting point. So you're probably talking at 90% of the melting point rather than 60 to 80. So this creates another issue. When you do this, aluminium has become very soft. There's something called a nil ductility point, and you're quite often going to hit that. So they become quite soft, and then they deform quite drastically. So there's quite a few challenges to overcome there. Yeah, so I've got a question here. What are the modes of load application? So in our furnace, we use a uniaxial hydraulic ram. It's just basically a hydraulic piston. Other people, there is a branch which I've got a slide about called hot isostatic pressing diffusion bonding, which uses pressurized gas. But there are potential ways to make jigs where you clamp your components and then you put them in a vacuum furnace, and then you can do some quite clever things with different materials which have a different coefficient of thermal expansion to apply a load. So there's a few different ways there to apply load. What about hardness tests in the mechanical? Yes, we can do hardness testing. You're correct. But because we're quite often doing a mechanical test, a tensile test isn't often not the need to do a hardness test unless we're doing a transient liquid phase bonds. You'd want to do a series of micro hardness indents through the joint itself, through the bond line, to see if you created any particularly hard or brittle phases. How do you decide the load and temperature? Yeah, good question. So a lot of this is there's a combination of looking at what exists in the prior literature, prior art, see what information we have. Also consideration of the alloy itself. They'll have a certain solidus and liquidus. Certain alloys will have a phase change, such as titanium. So you try to avoid the alpha beta transist temperature, for example. So it all depends on your material, but the ultimately we carry out small scale trials. So it's like an iterative process. You'll probably need between 5 and 10 samples to try to narrow down your processing parameters before you go to sort of larger scale. Right, so if diffusion bonding of aluminium is so difficult, why do we actually want to do it? So the reason is that there's a few distinct advantages that diffusion bonding of aluminium alloys have. And the first one is it's a autogenous joining process. So that means there's no additional materials unless you have an interlayer, like I said. But if you don't have an interlayer, it leads to increased corrosion resistance. But also, aluminium alloys have a high strength to weight ratio. So that means you can have lighter structures. And that's very big news at the moment in Europe in particular, because we have some very strict emissions targets to hit by 2030. So anything which can help to lightweight your structures is considered very seriously. But I think the main reason is diffusion bonding of aluminium enables you to manufacture parts which would otherwise be impossible. So you can have intricate internal features, you can form structures with complex internal 3D shape, you can create things which are more compact, so you're saving space, but you can also integrate other functions into your heat exchanger. And the other thing is, because you're making more compact parts, you're using less material. So there's quite a few benefits to aluminium diffusion bonding. So is it actually possible? And the good news is, yes, it is. And there are 3 general approaches which I will briefly discuss. So the first one is to apply a large load, induce large deformation into the sample. This will disrupt the oxide layer and allow diffusion between the different layers. The issue with this is, if you have intricate features, such as in this image here, you have these tiny channels, if you apply a load which is too high, they will deform and turn into sort of very thin crescent shapes, and they'll lose their functionality. So there's a limit to how far you can take this. The second thing would be to use interlayers to form your low melting point phase. So typical materials which are compatible with aluminium include copper, zinc, and silver, but each of these have their own issues. So copper, you can form brittle intermetallic phases. Zinc is not vacuum compatible. What I mean by that is zinc has all materials have a property called a vapor pressure limit. So that means at a certain temperature, in a high vacuum, the material will just dissolve from the surface. It will become a gas. And zinc does that at very low temperatures and very low vacuums. So zinc is not compatible in a vacuum furnace unless you use a partial pressure of inert gas. But then silver has an issue as well. So silver works very, very well, but the problem is it's expensive. If you imagine you had a structure with 200 different shims, you'd have to have 200 separate sheets of silver, so it becomes quite expensive. So the third approach is to remove the surface oxide in an oxygen-free environment. And that in itself is not too difficult to do. There's many different processes for removing your oxide. But the issue is, how do you load this into the furnace without exposing it to oxygen? There's the issue. And the problem with aluminium is the oxide layer will grow in less than a second. Not to the full thickness, but a significant enough layer will form in a second. So it might take you 10 minutes to load into the furnace. You're going to have oxide present. So yeah, all of these techniques have issues. They're either difficult to apply, difficult to scale up, or there's corrosion issues with the interlayers. So this is where TWI has developed some proprietary technology. We've actually developed a diffusion bonding technique where we can bond aluminium without the use of any interlayers and using a low applied pressure. We're actually creating a completely autogenous joint. So we've got a couple of examples here. This is a block of tiles that we've diffusion bonded together. And when you cut that in half and look at the section, you can see here the material is completely consolidated into one solid lump, and you can't see any of the bond lines. We've done a lot of work for one of our clients in a single client project, so I can't talk too much about this, but what I can say is we have scaled this process up to full-scale heat exchangers. And in the images here, I should add, we're looking at 6082 grade, so 6000 series. So yeah, at the bottom here, I can't discuss the precise process we use because this is TWI's intellectual property. But what I can talk about is we have an ongoing exploratory project where we're investigating 6082 and 2024 alloys. I see there's a few more questions. I'll have a quick look at these. Have you tried joining titanium and nickel alloys using DB? I haven't specifically. Titanium alloys are very easy to diffusion bond. They're one of the nicest materials. The biggest issue with them is they're very susceptible to any oxygen contamination, so you have to be very careful. Nickel alloys Also, our diffusion bondable, you've got to be very careful with what the grade is, because some of them have quite a few additives in there, and they've got very specific microstructures which you might disrupt. But generally, nickel alloys are diffusion bonded at high temperature. Titanium alloys, depends on the grade. Again, this is very grade specific. Often have an alpha beta transist temperature you don't want to go above. So you've got an issue here where you can't take the titanium too high. So looking at those two materials, you're probably looking at some sort of transient liquid phase type diffusion bonding process using some sort of interlayers. What hardness can we expect for typical alloyed steels like 4130 in diffusion bonded area? Okay, right. Yeah, so when we're diffusion bonding, we have no HAZ. The entire part is heated uniformly. So the entire component is heated. So there's no difference at the bond line, but you will, depending on the temperature you diffusion bond at, and depending on how long you hold it there, you might expect some softening of your material. And looking at NACE requirements, I've never had I've never looked into these NACE requirements. So actually look at so there will be no issue with hardness. Yeah. Compared to other solid state welding processes, how much is the joint strength as far as the similar material, so like ALTI system? So is the joint strength. So for a lot of the diffusion bonded joints, the diffusion bonded joint can be the weakest part, but it's not always the case. Like the example I showed earlier, actually failed in the parent material. We like to get to around 90% of parent material strength or higher. So whilst they might be slightly lower strength, they're generally, and if you've done the process properly, removed all your voids, they're as good as the parent material. So they shouldn't create any sort of failure concerns specifically. Right, go on to the next slide. So development work. We've worked with an aerospace partner to implement this technology into a compact heat exchanger, looking at 6061 grade. We have actually made a full-scale prototype, which I can't share, but in this image here is a small-scale prototype we made. So here's the diffusion bonded block we actually made at TWI, and they welded these fixtures and fittings onto the side. So you can sort of see where the technology has gone, where it's going. I will quickly address what I call the elephant in the room. Another method which can be used to manufacture aluminium heat exchangers is vacuum brazing. So for these, you get these plate heat exchangers which are made by vacuum brazing. How this is done is the aluminium sheets are clad in a different aluminium alloy, a lower melting point one. But the problem with vacuum brazing is you have a large molten phase present. Diffusion bonding has the following advantages over a brazed heat exchanger. So firstly, diffusion bonding can incorporate smaller features. This is because there's no molten phase, so you can have smaller features. There's less of a risk of the molten material filling your features. If you don't control your brazing process properly, you can have that issue. Also, if we're doing a solid state diffusion bonded joint, we have improved corrosion resistance. And as I said earlier, you can get basically close to parent strength properties, so you can actually run the heat exchangers at higher pressure, meaning they're more efficient. Well, have a look at the questions again quickly. Is the similar joint of Ti-Ni, so titanium to nickel, feasible through diffusion bonding? I'd have to have a look at that one. It's not one I've looked at. I'd have to look at the literature. I've not come across a combination of materials where it's not possible, though, with some clever thinking and some clever application of suitable interlayers. So I'd have to look into that one specifically. What kind of surface preparation and finish is required for diffusion bonding? Very good question. So that ultimately is, again, as with most of these answers, is dependent on the materials and the grades and the process you're using. If you're using a transient liquid phase process, you can get away with slightly rougher, slightly less parallel surfaces because you have the molten phase. But typically speaking, if you're doing a solid state generic diffusion bond, you want your surface roughness to be sub-micron. So I like to go for 0.4 micron RA or better. And with the flatness, again, you want it very, very flat. So you're sort of talking again in the sort of, well, if you're aware of optical flat measurements, there's something called light bands, and we like to go for better than 4 or 5 light bands of flatness, generally speaking. So we're looking at very sort of smooth, flat surfaces to give us the best chance of a good bond. But like I said, some materials are more ductile than others, so you can get away with a worse surface finish for certain materials. Right, I'm now going to discuss some generic applications for diffusion bonding. So again, I just want to reiterate what the benefits are before I go into the applications. So diffusion bonding allows flexible design possibilities, so we can have complex designs and it's an additive process. And we can incorporate small internal features. So look at the bottom right, this is a very complex heat exchanger, which wouldn't be very easy to make using other processes. And the picture on the top right here is a more industrial scale diffusion bonding furnace. So yeah, again, the other benefits are we've got an autogenous joint, so it's more corrosion resistant, and we can have high integrity, leak tight, strong joints formed by diffusion bonding. So one big area that we do a lot of work in is the use of compact heat exchangers in the aerospace industry. The aerospace industry has the requirements for lighter heat exchangers. And the next generation of jet engines, such as the turbofan engines being developed, also the ultrafan, I should say, ultrafan engines being developed by Rolls-Royce, are going to be running hotter. So you need to have them, you need to have heat exchangers which are more efficient and more effective at dissipating the heat. The other problem is these newer ultrafan engines are going to have larger fans, as you can see in this image, got absolutely huge fan diameter. So there's less actual room in the engine. If the nacelles are too large, the actual plane won't be stable. So you've got this difficult situation, less room, but you need to remove more heat. So the only way to do that is through the use of compact heat exchangers. So you're maximizing the heat transfer in a smaller unit. The problem is a lot of the traditionally diffusion bonded alloys are relatively heavy, so development of aluminium is quite exciting for this application. But yeah, the compact heat exchangers, because of their laminated nature, can be tailor-made to make use of some quite unusual spaces and shapes and sizes of space inside the engine. They don't have to be rectangular; they can be any shape you like. The compact heat exchanger can actually incorporate pipe work and other functions into the actual unit itself. So it's a nice flexible technology which can be used in the aerospace industry. A few more questions are coming, so I'm going to have a quick look at these. Yeah, so I've got a question. How do we determine which interlayers to use for transient liquid phase diffusion bonding? Again, so we start off by looking at papers and published articles be the first place to look, but then you also need to look at the phase diagrams of your materials as well. Just sort of try to work out if you're going to form any eutectic phases. But yeah, first thing really is literature, then it's small scale studies, and then examination. Have you formed any brittle intermetallic phases? So we're looking at SEM, we're looking at hardness testing, all this sort of stuff. So you can have a best guess, but you ultimately have to test to determine. Is diffusion bonding accepted by international codes and standards? This isn't something I'm not particularly familiar with. My manager does a lot of work in this area, and he is trying to push diffusion bonding more into these sort of design codes and actually standards. What I would say, diffusion bonding doesn't really have an actual standard anyway to manufacture parts, so I doubt it will be in ASME or DNV. So this is something being looked at by my manager at the moment. Can reheating a diffusion bonding product lead to a disbond? Yes, it can. So certain materials, when you heat them and quench them, will deform quite a lot. So you do run the risk of debonding layers. Your material, the actual process you use, you can tailor it to make it to induce less stresses in your components. Big one is how you design your components in the first place. Try to remove corners and stress raisers. But the final one is to make sure you've got a decent diffusion bond. If there's no voids or nothing for a crack to initiate on, the chance of it ripping apart is lower. but it is a particular problem for aluminium alloys, that is. So that's a good question. So when diffusion bonding, how do cooling rates play a role? Well, faster cooling, yeah. So we would love to have a diffusion bonding facility where we have a fast cool function, because as you say, you'd be able to maintain some of your materials properties and not have to do any post-processing. But our furnace does not have this facility, so we have to get around that by doing post-processing. But what I would say, we've had some very good success where if you select the temperature and the hold time, you don't actually have to do any heat treatment afterwards if you're careful. The only material which doesn't follow that trend is aluminium alloys. They come out in the fully annealed condition pretty much, so they need to be heat treated. Now, things like steel, you get a very minor reduction, like 5% or less reduction in strength, so you don't actually have to worry. So yeah, back onto the presentation. Some other applications for heat exchangers, as you guys are probably aware, they're everywhere. So automotive industry, lubricant oil coolers, water coolers, or heat recovery systems, such as the exhaust gas recirculation cooler. Plant and power industry, got loads of requirements for waste heat recovery, or for the cooling of generators or steam turbines. There's also a new market opening up around the hydrogen economy, and also supercritical CO2 stations for oil and gas. They need heat exchangers and they're operating in very extreme environments. So a diffusion bonded heat exchanger could be useful to those guys. And sort of more generic use could be the food and beverage industry. There's a lot of heating up and cooling down of fluids in these industries, so they need lots of heat exchangers. And the last one is what's it called? Ventilation and air conditioning systems, such as data centers. So another sort of diffusion bonding based process is superplastic forming, which I'm going to quickly touch on. Superplastic forming, some materials and alloys have a very unique property, and that is they stretch and they form without tearing if you heat it to an elevated temperature and you apply a load. So only some materials do this, but you can take advantage of this phenomenon to make some complex internal structures, as shown in the image here. But common materials which are superplastically formed include titanium and titanium alloys, and also it is possible to do on aluminium alloys. One of the common things which links these materials together is a very fine-grained microstructure. So this is actually used quite a bit in the aerospace industry, and it's used to make hollow turbine blades, for example. But the way it works, you start off by diffusion bonding. So you have your different sheets, and you apply something called stop-off. And what the stop-off does, it prevents a diffusion bond. So when you put the layer on top of this, it will only bond in the green regions, and the blue regions are not bonded. You then apply an internal pressure of hot gas, and that will then blow up this structure into a 3D shape. So that's all enabled by a combination of diffusion bonding and your stop-off. So this is typically carried out, this is for titanium, 900 to 930 degrees C. It's carried out in argon, and the pressure of the gas is 2 to 4 megapascals, and we get a strain rate. So strain rate is very important for superplastic forming, is 1.5 times 10 to the minus 4 per second. So quite a relatively slowish strain rate. So yeah, trying to think what else to say on this. Yeah, so it's quite often referred to as SPF DB, so superplastic forming diffusion bonding. There, so yeah, SPF DB. So that's a sort of niche application of diffusion bonding to be aware of. Got another one here. Let's see if I've got any more questions first. Will diffusion bonding withstand its working environment if it's at a lower temperature? I think what you're saying is, are diffusion bonds better at lower temperatures? Would diffusion withstand if working? I think the answer to that is yes. I think it all depends on the materials you've selected, which grade you're looking at, because yeah, it all depends on the joints and your actual environment. So I'm going to go on to another very sort of unique type, sort of sub branch of the diffusion bonding family. And that's something called electrostatic bonding. So this has been used since the 1960s for joining silicon to glass. And this is very similar to other diffusion bonding processes because you require the surfaces to be very clean, very flat. The components here, so if this is our electrostatic diffusion bonding kit at TWI. This plate here, these plates move together, and your part here in the middle is what's diffusion bonded. And then once these plates come together, a big shell comes down over the top, and that's your vacuum vessel. But what we do, these are typically bonded at 3 MPa, and that's about 400 degrees Celsius. And once you're at your top temperature, you actually apply a DC voltage of around 100 volts to the parts, and that and with your metallic components being held in the positive. So you need the electric current for this to work. The other thing you need is, for electrostatic bonding to work, you need mobile ions such as sodium in the glass for it to work. Other than that, I don't actually know too much about this. Our electrostatic bonding kit hasn't been used for around 6 years, so I've never looked at this myself, but it is some other alternative diffusion bonding process I thought you guys would be interested in. But I couldn't ask too many questions on that, unfortunately. So another sub-branch is hot isostatic pressing, known as hipping for short. So the fundamentals of this, it's very similar to uniaxial diffusion bonding, where you're heating up materials and you're applying a load to them. But what is different is how you apply the load. So rather than a hydraulic ram, you're using a pressurized gas to apply your load, and that's commonly argon. And this creates an isostatic load on your parts. That means it's getting squashed from every single direction rather than just one direction. And the pressures that are used are typically really high. You can get up to sort of 1,000 or 2,000 bar, which is why you see in the image, this is an example of a HIP furnace. You've got your furnace here, and you have a massive yoke around the outside just to maintain to keep the pressure inside the vessel. All of that is just strength and reinforcements. So you can get some ridiculously high pressures. So you can use hipping to join solid parts together, but we quite often look at using hipping to consolidate and join together powdered material. So common applications for hipping include hard facing. So you can put a wear-resistant material on, or a corrosion-resistant material onto steel, for example. This is quite often used in the paper mill industry and the plastic extrusion industries. You can use it to densify additively manufactured parts. So you can take components you 3D printed using laser additive manufacture, for example, put it into your hip, and it will then remove all porosity from your parts. But you can also use hipping as an alternative to casting. So you can design and develop these types of cans, which have an intricate internal shape, fill with powder, hip, and you've basically got a cast part with no porosity. This is especially useful for higher performance applications, or where you want to create a material which doesn't exist using wrought or cast processes. So sort of difficult to manufacture alloys, you can hip. So you just change your mix of your powder you're using. And it also can be used to fabricate metal matrix composite materials. I'll go back to the questions. Reason I'm doing it as I go through, I don't want a load of questions at the end. I think I'll do it as I go through. So can a diffusion bonding product that has debonded during service be rediffusion bonded? Yes, so that good question. Again, it all basically comes down to the materials again. But essentially, if your parts have been in service and failed, there's a chance that the surfaces have become contaminated. So if you've got a non-flat surface or a non-clean surface, I think diffusion bonding it back will be challenging. We have had a go at doing that before with limited success, but I think it all comes down to the individual scenario, I would say. How to repair defects in diffusion bond? Well, essentially, with diffusion bonding, when you're developing your parameters and your processes, you're trying to get to the stage where there are no defects. You've got these complex structures, internal features. There's no way to access them. So there's no way to repair them. But it's all down to careful loading, careful preparation of materials, very high level QA, quality assurance, very in-depth inspection procedures. For example, if you're making a heat exchanger, you'd look for scratches on the surface. You'd reject anything with a scratch. You need special lighting, sort of, white light type facility to inspect your parts. So it all comes down to QA, QC to reduce the likelihood of a failure. But what I would say is, once we developed a process and we got it working, I've never seen one where we do have a random failure which cannot be explained. So diffusion bonded using laser shock is ever tried anywhere? I must admit, I don't know what laser shock means. If you can elaborate, I can try and answer that question later. Right, back to the presentation. So yeah, some other generic applications. One is a cryogenic heat exchanger. So on the right-hand side is an example of a cryogenic heat exchanger. This is not diffusion bonded. This is a traditional tube type one. But imagine if you could try to make this complex structure into a compact heat exchanger. So I think aluminium alloys will be very good for this because they're because of the structure, the crystal structure of aluminium, they do not become brittle at lower temperatures, and actually, in some cases, become ever so slightly stronger. So I see a really good opportunity to use aluminium alloy diffusion bonded heat exchangers for where liquid hydrogen, nitrogen, helium, or oxygen is used. Could also be used for superconductor type applications or in the liquefied natural gas industry. So they're the two sectors I'm looking at. Other applications include process intensification, particularly for the petrochemical industry. And what I mean by this is a lot of these petrochemical processes have a lot of waste heat and waste gases. So it's trying to use that and bring it back into the system to increase efficiency. That's what process intensification. Instead of just losing your heat, let's use it to do something else. You can use that to intensify your process, to save money, make it more efficient, that kind of thing. Another area where we've had quite a bit of what's the word? We've done quite a few projects recently, the electronics industry. So a lot of machines and equipment which are used to manufacture semiconductors make use of some very complex structures, which kind of like shower heads, but they're not. It's much more complex than a shower head, but lots of structures with very small holes, and they can be vacuum brazed or diffusion bonded together. Same for machines which carry out atomic layer deposition. They need very precise sized and shaped nozzles, so maybe diffusion bonding can be used for that. We've used it recently to join fine meshes together, and we've also looked at busbar manufacturing. So the real driver there is trying to join dissimilar materials to create transition pieces, the busbars. Other applications include microsystem technology. So what I mean by this is there's a whole new area of 3D printing and additive manufacturing, but control and quantification and sizing of the particles is very important. And what you could do is you could use diffusion bonding to make fine channel filters for your powders. So you could say any particle over 0.5 microns cannot get through the sieve. So you filter out your larger particles. So particle sieves and fine channel filters. Another area is injection molding dies. So on the right-hand side, we've got two approaches. On the left is traditional. So you've got some pipes in your die. On the right-hand side, you've got your additively manufactured part, or your diffusion bonded part. And as you can see between the two, the channels here are much closer to the surface of the die. This is called conformal cooling. It's trying to get your heat transfer as efficient as possible. And this is very, very big news in the injection molding industry because tool wear is an important consideration. As you can see, the tool here is much hotter compared to the conformally cooled version, but also the quality of the parts which are injection molded is much higher quality if you can get the tool to be colder. So you're improving, you're increasing the life of your die, and you're improving the quality of your injection molded parts. And nowadays, I don't know if you guys have ever seen this, there's some very, very intricate stuff being injection molded. There's some very tiny, very fine features. They're really pushing the boundaries. Conformal cooling helps to enable this. But yeah, just to sort of summarize, any product where you have a complex network of 3D features or difficult to machine internal features, where you're trying to improve performance or functionality, you can use diffusion bonding. Anywhere you've got a fluid or a gas you're trying to transport, you can use diffusion bonding. So I'll go back to the questions again. So what is the difference between diffusion bonding and roll bonding? Yeah, roll bonding is very similar, because you're heating material and you're applying the load and you're rolling it. The main difference is the time. Diffusion bonding is generally speaking, a process which has a longer hold time. And with roll bonding, you're trying to sort of create things like braze alloys with an interlayer or sandwich structures you're going to use somewhere else. You're trying to create something thin. Diffusion bonding is looking more at 3D sort of structures, but you could consider roll bonding as a subset of diffusion bonding. So that's certainly true. Can diffusion bonding be used to join tubes to tube sheets in shell and tube heat exchangers? Uniaxial diffusion bonding, no, but there's no reason you couldn't look at using hipping. The issue is going to be what size is your shell and tube heat exchanger. If it doesn't fit inside the HIP furnace, then you've got no chance. But I think generally with diffusion bonding, we're trying to get away from tube to tube sheet heat exchangers. We're trying to replace those with compact heat exchangers. So that's kind of the drive of the technology. Right, so I'm going to do some specific case studies now, go through a few examples. So this first one is quite basic, but it leads on to the next case studies. I thought it was important. Before I go through the details, actually, what I will do, because we've got a nice image of the furnace here with it open, I can talk through some of the pieces of the furnace. So this is the vessel itself, and inside there's a box, and this box is called the hot zone. This is made out of steel with on the outside. You have a thick layer of graphite on the outside, which is the insulation. And this is your working zone. Whatever you diffusion bond has to be inside the box. Because if you look, your elements, there's one here, there's one on the door, and there's one this side and one at the back. So your elements are inside the hot zone around the job. The actual piece we're trying to diffusion bond in this image is the very thin piece in the middle. The rest of this material here is graphite tooling, and the whole purpose of it is just to apply the load to the job. So the ram is here at the bottom, it comes up and it reacts on this point here. So there's the internals of our diffusion bonding furnace. And you see a vacuum gauge at the top there, water cooling pipes, and a controller at the bottom. So that's our diffusion bonding furnace. But anyway, we carried out a core research program to look at diffusion bonding of stainless steel. And we developed a set of parameters, so temperature, time, and load. And we actually found temperature had the largest effect, which is very obvious when you think about it, because diffusion is a firmly activated process. What I mean by this is a 10% increase in temperature has a larger effect than a 10% increase in load or pressure. So temperature is very important. And here are some micrographs of what we managed to diffusion bond. So the first set of parameters, you can see the bond line is very visible. There are quite a few voids present, so that's not a very good joint. We modified the parameters and we got something which looked better. Then we refined even further to get to this stage here where the bond line is mostly disappeared. You can only see a few voids, but more importantly, you're seeing grain growth across the boundary. So very clear signs of grain growth. So that there is a good example of a diffusion bonded joint. And you can actually see the size of the pores aren't too dissimilar from the size of the sort of intermetallics or pores in the parent material anyway. So it's very difficult to see. So in this project, we were able to diffusion bond 316 such that there was minimal residual porosity at the bond line. We achieved a diffusion bonded joint strength equivalent to that of heat treated parent material 316. So what I mean by that is you can't compare your as received to your diffusion bonded. You got to heat the part as well to make a comparison. But we basically got parent material strength, and we got significant elongation in the samples. You can see the ductility here. You can see the tearing and the ductile failure, which tells us the bond is very good. We got a ductile failure rather than a brittle fracture. Before I go on to the next bit, I'll look at a couple more questions. Can diffusion bonding be used to fuse porosity and or blowholes in products, example castings? I've not seen uniaxial bonding used in this way, but if you consider hipping to be a diffusion bonding process, then yes, you can use hipping potentially to consolidate castings. Again, I've seen it mainly with 3D printed parts. I've not explored generically casted parts, but we do have I don't get involved too much in the hipping powder side of things, but we do have experts in the team who could discuss that further if you're interested. Can we diffusion bond between different metals? Yes, we can. Yep. So if we're lucky, we can diffusion bond different materials using no interlayers, so a solid bond. But that's number of alloys where they're compatible is few and far between. There are a few though, but quite often you need to use an interlayer to create a transient liquid phase diffusion bond, or you could try to make use of a eutectic phase if it exists for those different materials. So it all depends on your combination of what approach we would take. Is chromium oxide layer a hindrance to diffusion? Yeah, so we're lucky with stainless steel diffusion bonding. It's performed at a high temperature. It's performed above 1000 degrees Celsius. So it's anywhere between 1000 and 1250, somewhere between, depends on the grade. But at those temperatures, the oxide layer fully dissolves into your parent material, so we don't have to worry about it. What we do have to worry about, though, is chromium has a relatively low vapor pressure. So what that means is if we, during diffusion bonding, we can actually lose chromium from the surface. It will vaporize off the surface and deposit itself somewhere else in the furnace. So you might want to consider diffusion bonding under a partial pressure of gas to lower the vacuum. So yeah, but chromium oxide is not a problem, generally speaking. Right, so I'm going to go through another case study now. This is a European collaborative project we carried out called Renew X. This is supposed to resemble an X, these two arrows. So yeah, brief overview. There are 200 million households in Europe. All of these have domestic heating needs, and it actually accounts for around 30% of the whole of Europe's energy demand. So if we need to try and reduce this to achieve the emission reduction targets set for 2020. So we should add, this project was carried out around a decade ago. So that's why it's saying 2020 targets. And the other thing as well, from a sort of security point of view, Europe wants to try to decrease reliance on imported energy from places like Russia, for example. So one solution is to use more renewable energy. And we're sort of looking at instead of a conventional boiler type system for a house, there's something more efficient called a heat pump. And these are sort of new, well, as of a decade ago, newer systems to heat your home. So the challenges were several of these. Electrical heat pumps are expensive compared to your modern condensing boilers. The assumption was when this project began, there's going to be no subsidies for these units. So heat pumps, for them to be economically viable, have to significantly outperform a traditional boiler or a gas-based alternative, so a gas boiler. If it's expensive and more expensive, it's got to be better for people to buy it. So in order to do this, the key area to improve was the conventional finned tube heat exchanger in the actual air pump itself, so air source heat pump. And here's a picture of one on the side of a house. So you'd have this instead of your condensing boiler in your home. So the consortium, you can see here, there's a group of SMEs from around Europe who were involved, group of research companies. So that's where we stepped in. There's also Newcastle University involved, and we had a few end users as well. The important one here being Advanced Chemical Etching, ACE, who did a photochemical etching of the shims. Essentially, in the initial phase of the project, it soon became very apparent that a good way to replace the traditional heat exchangers is to use a compact heat exchanger. And the literature reviews and discussions amongst the consortium eventually decided on a 316 stainless steel heat exchanger. So this was really good for us because we carried out that research program, which we've already discussed. So we already had the data. But basically, the way these parts work is you have your photochemically etched shims, which you stack together to create your complex geometry. And these can then operate at high pressure and are leak tight. So the advantages of these heat exchangers over the conventional thin type heat exchangers are they're smaller, lighter, they're a single block of material, there's no galvanic or no potential for galvanic corrosion, and they are corrosion resistant because of that. So they are the advantages. And here are some, I've shown this image already. These images come from the RenewX program. So we actually made some compact heat exchangers. And again, so they vary your photochemically etched shims. You stack them together, you diffusion bond them, and here are your channels. What I would say in this image, ignore the particles inside the channels. This is just where, when it's been cut, material is smeared over. So that's an effect of metallography. But yeah, there's your channels. It shows the principle. So the lessons of this project, some very big lessons. Alignment was very critical. Because we have very tiny features, you can see here how small the channels are. If you are slightly out by a tenth of a millimeter, you can have an issue. So building in some sort of alignment feature, such as a pin or a rod, as shown in this image here, is important. It's very important to balance your parameters, so you're getting really good strength for your joints, but you're not excessively deforming your channels. So you've got to balance strength versus deformation. You need to think about the condition of your material post bonding. If it is too soft or too weak, you might want to tweak your process, make it a shorter hold time or a lower temperature, or consider post-processing. These ones here were fine in the diffusion bonded state. They passed all strength criteria, so they needed no processing. The designs of the shims themselves is important. In fact, I've not really discussed this yet. If I go back a slide, when we're applying the load has to go through each individual layer. And if you have any dead zones or dead regions, you will not get a bond. So if you've got a huge hole here, let's say, the layer underneath will not bond. So you need to really carefully design each layer to ensure that the load is transferred through the entire stack to ensure that every layer is diffusion bonded well. So that's very important. In fact, I reckon for heat exchangers, shim design is the most important thing, actually. You can play with the parameters, but the design is harder to change once you've made your parts. So here is the key part. But also, diffusion bonding can be used to, the final lesson was diffusion bonding is a process which we can use to make micro-channel heat exchangers, which was a great outcome for the project. So I'll look at the questions before I go on to this example. Is there a reliable process for bonding titanium to steel or aluminium to steel? Again, this is, aluminium to steel I know is difficult. You need to use quite a clever arrangements of interlayers for that one, because you can get some quite brittle intermetallics. Titanium to steel, we've had that already, I believe, that question. For ship superstructures, they're probably going to get, as I imagine, a lot of these parts are going to be very, very large. So if they don't fit into a furnace, you're not going to be able to diffusion bond using these processes. But as someone alluded to earlier, there is hot rolling, so that could be a process which is applicable. Can a diffusion bond product pass the hydrogen disbonding test? Yes, it can. We've actually done some trials. We've made a, try to think what I can say. We have done tests and trials on heat exchangers in hydrogen, and they've passed. So yes, they can. I can't say much more than that, though, unfortunately. In the 316 diffusion bonding experiments, where did the failure occur in testing in perimetal diffusion interface? I'll be honest, I don't know the answer to that question because I didn't carry out that program of work. I have done some work on 316 stainless, and it's variable. It depends on the parameters. So it can fail at the interface or it can fail in the parent material. It was a bit of a mixed bag. Depends on how well your bond or how good your bond is. What is the acceptability of this process in BPV codes, ASME? As I said earlier, I don't think it's recognised, and it's something we're looking into. We're discussing with the different authorities and standards bodies about diffusion bonding. But it's currently more used in niche applications, which is why it's not found its way into standards or codes yet. Where are we? Can diffusion bonding coherence be subject to forming, e.g. It's not something I've looked at, actually, but if your bond is good enough and high strength, I don't see any reason why you couldn't do some sort of forming process afterwards. I'm trying to think. Actually, no, we have done a project. Yes, we did a project where we diffusion bonded some parts, which are quite thick. And these were then cut down and rolled into much thinner components, and they survived. So yes, you can do some forming processes if your bond is good enough. What are limitations compared to roll bonding or explosion bonding? Yeah, I think explosion bonding is interesting because you can bond some pretty large sheets using that process. And the other advantage of it is it's quick. It's a quick process, so the risk of softening your parent material is less. The issue with it, it's a very dangerous process, and it's not done very commonly. I don't think we do it in Europe. We might do it in one place in Germany, but I know the Americans are very big on explosion bonding. But I wouldn't use explosion bonding to make a heat exchanger. It's more for making sheets of material which are dissimilar, I would suggest. And same with roll bonding. So DB, think more complex 3D structures. Roll bonding and explosion bonding, to think about more sheets of material, which are sort of clad materials, let's say. Another question, if furnace size is not a concern, what will be the largest size that can be diffusion bonded? Well, probably no limitation, to be honest with you, as long as you can make sure your load is applied uniformly. But the problem is you have to do this in a vacuum or in an atmosphere, so there is probably going to be some type of limitation. Again, it depends on your components and what you're looking at, because like you said, there's roll bonding and all sorts of other processes. So again, it's very specific to your application. Do you have any experience of welding duplex pipes using diffusion bonding? I have looked at it. That one's very difficult because you have to cool down duplex materials very quickly. So you will form sigma phase, but you can heat treat them afterwards. So yes, we have looked at it, but you do have to do post-processing afterwards to get your ferrite austenite structure back to 50-50 and to try to remove your sigma phase. But it is possible. Right, so back onto this example, combustion chamber. So we carried out a project for the European Space Agency, or ESA, and the idea is to look at using ceramics in rocket engines. So at the moment, they use C103, which is a niobium alloy with hafnium, and it has a special coating on the surface, so it can operate at temperatures up to 1,350 degrees Celsius. But there's an interesting ceramic material. Well, there's quite a few interesting ceramic materials. One of them of particular interest is silicon nitride, but this can go up to even higher temperatures of 1,500 degrees Celsius. So that would make it even more attractive for rocket combustion chambers. So the question is, can you join C103 to silicon nitride? So the answer is yes, we can. We looked at vacuum brazing processes and also diffusion bonding. It's actually a transient liquid phase process. You can see the parts we made here. So we have the ceramic and the metal formed into rings. And there's one of our technicians next to one of our furnaces with the parts. So in this project, we were able to join these dissimilar materials. We used ring shapes just to represent the geometry of the thruster chamber, but that was a very good, successful project. Another example of diffusion bonding in industry. So yeah, sort of more generally speaking, TWI is currently working with a range of different space companies to investigate the use of powder metallurgy for space applications. So working with a range of different companies, but we're looking at uniaxial hot pressing and hot hydrostatic pressing to assist with this project. So currently down selecting these processes at the moment. So, right, okay, so we're nearly end. Let's go for a couple more questions. I'll do the conclusions. Can we join two diffusion bonded products by welding? Yes, you can. There's that image I showed of the. In fact, let me go back to it actually. There's a few slides back. Here you go. So this is a diffusion bonded heat exchanger, and it's been directly welded to on the sides. So yes, you can. Have to be careful though of your heat inputs and what sort of strains and stresses you're putting on the parts. But if you're careful and you design your WPS and your PQRs and all that sort of stuff, yes, you can. I want to go back to the conclusion. So, yep, final slide. So in conclusion, diffusion bonding enables the joining of otherwise incompatible materials. It can be used to form some really complex shapes which you couldn't manufacture using other processes. And it's actually it's a joining process which can be applied to more applications than people initially realize. And as I keep saying, process conditions are king here. They are critical to your success of your diffusion bonded parts and where you can use it and where you can apply it. But it's this process, even though there's lots of potential applications, it is still a niche joining process, but it has the potential to be a much more commonly utilized manufacturing process. I will elaborate on a couple of things quickly. So diffusion bonding as a manufacturing process. The furnace itself, depends on the size you get, is anywhere between probably 350k up to £2 million. So they're very expensive pieces of kit. They're very sophisticated. You have hydraulic rams. You have a vacuum chamber. Some have fast cooling. So they're also a pressure chamber as well. So you have 10, I think it's up to 10 bar quench. So some of these facilities are very expensive. And the problem is it's a batch process. It's not a continuous manufacturing process. So this is suited. So I'm talking here about uniaxial diffusion bonding. It's suited to batch production, so lower volume parts, more niche, parts which need higher strength, higher integrity, higher complexity. So it's never going to replace welding. It's never going to replace your basic joining processes. So it is niche, but it has its place in the tools and arsenal of the engineer for creating certain components. But the other thing, there's a second elephant in the room I need to discuss, and that is additive manufacturing, 3D printing of metal materials. So you're probably thinking, why can't you just 3D print your heat exchanger? And the answer is yes, you can, but there's a few issues with 3D printed parts. One is controlling the surface condition of your internal features is very difficult. That's one issue. Second issue is entrapped powder. We've actually done projects where we've diffusion bonded 3D printed heat exchangers because they have to cut them in half to empty the powder, then we diffusion bond it afterwards. So you've got to think about how you're going to remove your excess powder. Thirdly, you do get porosity in 3D printed parts. What I would say is some of the new developments, actually, the porosity is very low. It looks very, very good, but you do have more porosity compared to a piece of sheet material which has been rolled and then photochemically etched. So there are a few issues with AM, but it is developing and it could become an alternative process to DB. But then there's also a project we're looking at where people are asking us to diffusion bond flanges onto 3D printed heat exchangers. So there's a bit of synergy here, sort of cross-pollination between the two processes. So I don't think the advance of 3D printing or AM will remove the need for DB or diffusion bonding. I think they could be quite symbiotic processes. But anyway, that's my presentation today. I hope you enjoyed that. I have a bad feeling I did speak quite fast at times, which I apologise for. But if you want to contact me with if I've not answered any questions in enough detail, it's my email address and my phone number. I will quickly look at some more questions that have come in. So, what is the minimum surface finish requirements for diffusion bonding? So, again, I said this before, it depends on the material. If you've got a molten phase, you can get away with a worse roughness. Generally speaking, if you're doing solid state diffusion bonding, you want it to be less than a micron RA. I try to go for half a micron or better if I can. So you want it to be very smooth. Not mirror finish, but smooth. What parameters do we have to monitor throughout the process? So we're looking at the main furnace parameters. So we're looking at temperature, cool time. We're looking at all the main furnace parameters, but the most important thing is quality control, looking at the actual parts before they're bonding and handling them very carefully so we don't introduce scratches or defects, anything like this. I think that's all the questions, actually. Is there any more? There's a couple more come through. What is the time frame required to get diffusion bonding recognised by ASME? I pass. I can't answer that one, unfortunately. It's one my manager is looking at, but he's talking to more British BS, ENISA just to get a standard. There is no standard for diffusion bonding. You can do what you want. There is nothing. So we're trying to get that sorted first before we go into the codes. But I could be wrong. There could be stuff in the codes already. I need to check that with my manager, but I've not personally looked into it. So can TDI share a few technical papers on the use of diffusion bonding in the petrochemical industry? What I would say to that question, contact me. If you're a member company of TWI, there may be something we can share. But if we've done anything with single clients, we can't share that. It have to be either core research or something more publicly available. I don't think on the top of my head I've got anything specifically, actually. But send me an email and we'll have a discussion about it. Another question here. During diffusion bonding process, how can we control temperature and load to avoid distortion or deformation? Very good question, actually. Very good. So there's two approaches. Either we limit the temperature and the time such that we don't get excessive distortion or deformation. But the problem with that is you might compromise the strength of your joint. So what you can do is you can design and use jigging, which has a stop in it. And what I mean by that is when deformation or the thickness of the unit gets to a certain point, it will hit a stop. So it could be a graphite block, it could be anything, but it will prevent the unit from deforming any further. So you can use physical stops to do that. So that's one thing we actually do use quite regularly. Minimum surface finish requirements for titanium alpha alloy. For titanium, because it's a solid state joint, I would say 0.5 microns or better RA would be my recommendation. What's the range and temperature at time for diffusion bonding? Infinity, basically. You can take any parameter as far as you want. And actually, diffusion bonding occurs naturally over time. If you have lead tiles on top of a church roof, for example, they will diffusion bond over a period of several centuries. They do. You see them come out solid. So you can vary them as much as you want, but you're trying to balance things like deformation, time. You're trying to balance all these different parameters. So generally speaking, you're looking at 60 to 80% of your melting point for temperature. Time, you want it between 1 or 4 hours. And yeah. Can we carry out heat treatment after DB? Yes, you can. Yeah, I think that's every question for now.
Thanks, James. Thanks a lot. It was a wonderful presentation, and with the number of questions, you can see people are really engaged in the presentation, and you were answering the questions as you go,
yep.
Which I think much more better for the people to ask one question myself. I would like to know, these heat sinks for the electrical components. So for IGBT or semi-controlled rectifiers, to cool them, we have an aluminum heat sink with a copper substrate on the top. Is it a possibility to do a diffusion bonding for applications like that?
Yes, it is. Yeah, that's actually become quite a hot topic recently, aluminium to copper. We've got actually just embarked on 2 separate Innovate UK projects on that subject. So yes, it is possible. There's several different techniques you can use. There's obviously interlayers are a possibility. And you can also make use. Aluminium and copper form 2 separate eutectic phases, one at the copper-rich end and one at the aluminium-rich end. So we're hoping we might be able to utilize that to diffusion bond it. But at this moment in time, we've not done any trials, but it's something we are currently working on. So yeah, if you want to find out more information, just let me know. We can discuss that in more detail.
Sure, I'll be in touch with you on that topic. And as you do some more research, or if you have some examples, it would be lovely to know. It's a big application field, and if you add copper to the aluminium, the heat dissipation increases and the efficiency of the heat sink goes up. That's where people want to work now, so that the devices could get smaller and smaller and more efficient. Thanks. I will now give it to Dr. Krishnan.
Yeah, thanks, James, for a wonderful presentation on diffusion bonding. I think all the participants really enjoyed. And now I request Mr. Ashok Malge, Secretary of the Indian Institute of Building Mumbai branch, for the vote of thanks. Over to you, Malge.
Good evening. This is Ashok Malge, Secretary, IIW India Mumbai branch. It is my privilege to propose vote of thanks on behalf of IIW Mumbai. I thank TWI for this tech talk on diffusion bonding opportunities and challenges. topic as far as the general purpose is concerned. But however, it was quite interesting and technically it was very, very uh, wonderful. Let me thank Chris for briefing on TWI and TWI activities in India. I thank Mr. James for having talked facilities, activities, diffusion bonding of different materials, example, aluminum alloys, stainless steel, other materials like including ceramics, with citing examples and applications like heat exchanger, aerospace in aerospace industry, etc. And he also explained with a few case studies on stainless steel, ceramics, silicon nitride. I think people who attended have gained a lot on this particular topic. I thank our technical team, Dr. Krishnan, Nimesh, and Abhishek for organizing this Well Tech Talk. Thanks to all participants for having joined this talk and having taken advantage of that. It was a wonderful talk, and I thank the team TWI. Thank you very much.
Thank you, sir. And we have enjoyed the opportunity, and hopefully we may have another one soon.
Thanks.
Yeah, we'll have some interactions in future.
Okay.
Nimesh, we were talking about the heat exchanger, and we made one aluminum base with about 98 serrations in a diameter of about 5 inches, and we had copper fins joined to them by diffusion bonding way back for CPU heatsink. And it's possible we may have to look into these details. We'll see how best something can be derived at.
Sure. So we would also like to interact with you and figure out, James, if induction heating can be used in many of these processes where, you can have a very controlled heat input and get that done. We manufacture induction heating power sources here in India. We are exporting to about 20-30 countries now. And that's another interesting way to look at controlled heating. And we're working on that for many applications, for brazing especially.
Yeah, we'd love to talk to you about that. So whenever you're ready, fire me an email. We can set up a conference call or whatever to discuss. Sounds good to me.
Sure, James. Thanks, James. Thanks, Chris. Have a great weekend. And thanks, everybody, for joining in and tuning in for another Well Tech Talk. Thanks.
Thank you. Thank you so much.
Yeah, we all will meet again.
Bye-bye.
Thanks, Chris and James.
Yeah.
Okay, thanks. Bye-bye.
Chris,
Bye.
thanks, Chris and James.
Thanks.
Thank you. Thank you, Krishnan, Nimesh, and Vishal. Abhishek.
Time to sign off all. Thank you. Bye.
Yeah, sign off.
Thank you.